Hello everybody. In this video we're going to discuss one of the very important discoveries that were made that were based on the fluid statics, and this was the determination of the atmospheric pressure. It was like a long time ago, around 400 years ago, an Italian scientist named Torricelli was able to perform a very simple but a very intelligent experiment that he proved using this experiment that the atmospheric pressure can be measured, and he determined the value of the atmospheric pressure. This setup or this experiment was called the Mercury barometer. The idea of the barometer is very simple. It consists of just two parts. A container that is filled with mercury, and there's a lot of mercury here, but the first is a container that's filled with mercury, and a graduated cylinder that it's a long graduated cylinder. It's around 1 meter or something, 1 meter high. And this graduated cylinder, and these are the only two things. So the setup starts by filling the graduated cylinder with mercury. So it's totally filled with mercury. And then the the graduated cylinder is flipped 180 degrees with the opening closed. So it's sealed, and it's flipped upside down. So the opening is down and the bottom is up. And then this flipped graduated cylinder is put in the mercury container, and then the sealing is removed, and that's it. This is the whole experiment. What they noticed when they did the experiments is that the mercury level, which was originally filling the whole graduated cylinder, it starts to move down, meaning that some of the mercury is drained from the graduated cylinder and fills the container, and it keeps going down until it reaches a certain height, and then it stops. The volume above the surface of mercury in the graduated cylinder is pure vacuum. It's a closed cylinder, so there is no way for air to go inside and fill this space. So this is pure vacuum that's above the surface of mercury, and that's it. This is the experiment. From this experiment, we were able, or the scientist Torricelli was able to calculate the pressure, the atmospheric pressure, given the basics of fluid statics. This is very simple. We know that the point D is exposed to the atmosphere, so the pressure at point D is atmospheric pressure. We know that point C is exposed to this space, which is pure vacuum. So the pressure here is 0 at point C. So the pressure at point C is 0. The pressure at point D is the atmospheric pressure that we do not know until this point. And we also know that points B and D are at the same level. We know that 2 points at the same level in the same continuous fluid will have the same pressure. So the pressure at point D and point B are equal. We know this is atmospheric pressure. Then the pressure at point B is also atmospheric pressure. And we can get a relation between the pressure at point B and C because there are 2 points in the same fluid at different depths. So we can get the pressure at point D in terms of the pressure at point C. We know this is 0, and we know this is atmospheric pressure, and we know the height. Okay, so this is simply what we have. So we have, we have the pressure at point B is equal to rho GH, which is 0 plus rho GH. Rho is the density of mercury times G times H. We know the pressure at point B also equals the atmospheric pressure. And by the way, the height H that was found experimentally is equal to 76 centimeter mercury or 706 millimeter mercury. And this is why, this is what we found, or what was found experimentally. So when we put the equations together, that pressure B equals pressure at point D and the pressure V equals rho GH, so we can find the value of the atmospheric pressure. This is equal to the atmospheric pressure and at the same time equals rho GH. So rho is the density of mercury, which is 13,595 kilograms per meter cube. G is 9.81 or 807 meters per second square, and the height is 0.76 meter. And so the pressure or the atmospheric pressure is 1.013 times 10 power 5 Pascal, which is a value that we know. So this is how we get the value of the atmospheric pressure from the height of a column of mercury that is 76 centimeter high. And by the way, this is why the value of or there is a unit of pressure that's millimeter mercury and centimeter mercury, because we know that 1 atmosphere is equivalent to 76 centimeter mercury or 760 millimeter mercury. So millimeter mercury and centimeter mercury can be considered as units of pressure. Okay, so these are the outputs of the experiment, and this is, and as I told you, it's a very simple, but it's a very smart experiment that was made to determine the value of the atmospheric pressure. Now there is a very important question. This is not in the textbook, but based on the my experience with the students, I feel that this is a point that needs to be made clear. Is the atmospheric pressure a big pressure, or is it small pressure? We might have a bad or a wrong idea about the atmospheric pressure, because our bodies are designed to withstand the atmospheric pressure. This is the pressure that we live in. This is the pressure that everything around us is exposed to. So we might think that atmospheric pressure is not a big deal. It's not a big thing, because this is what we have in our daily life. But actually, it's not. It's atmospheric pressure is a big pressure. To have a feeling of this, I found this interesting video. This is a tank that is filled with air. Okay, and it's a big tank. It's, I would say, I don't know how long is it, but I would say it's like 10 meters or might be longer. This is a tank that is filled with air, and it's connected to this tube here. This is connected to a huge compressor. This compressor will pull the air out of the tank, and as the air is pulled out, the pressure decreases inside the tank until it reaches a point that is very low. Okay, so now when the pressure inside the tank increases, it's now exposed to atmospheric pressure from outside and very low pressure from inside. In the current state, it's exposed to the atmospheric pressure from inside and outside. That's why it's in a state of equilibrium. There is no side that is exposed to more pressure than the other side, because every side, the inner and outer sides, are exposed to the same pressure. But when we pull the air out of the tank and the pressure decreases inside, then we have two different values of pressure. The inner pressure is very low, and the outer pressure is atmospheric pressure. So now we can see if the atmospheric pressure is strong enough to do some deformation to the tank or not. So this is what we will see now. As the pressure decreases, suddenly the tank collapses. This is very common thing in containers that are designed to or that are operating at low pressures, or it's sometimes called external pressure, and that's why there are special requirements that have to be met for the design of these tanks, and to be supporting rings to make sure that the tank is not going to collapse. But the point I want to make here, that this collapse that we saw in the tank, this strong deformation, is due to the atmospheric pressure. So atmospheric pressure is not small pressure. It's a big pressure. We are used to it, and our bodies can live safely under the atmospheric pressure, but it's a big deal. And this is what I want to make out of this slide, and I hope this makes the point clear. There is one more thing that we need to know about atmospheric pressure. I think it's a known piece of information, but it's good to mention here that the atmospheric pressure is a result of the it's like any other fluid. It's the result of the height of the fluid, and as we go deeper, the pressure increases. So this is what we have. or we have also for the atmospheric pressure. The atmospheric pressure is a result of the height of the air acting on whatever or acting on specific height. So what we know about the atmospheric pressure, which is 1.013 times 10 power 5 Pascal or 101.3 kilopascal, is at sea level. So as we go up with altitude, for instance, for 1 kilometer, it's going to be almost 90 kilopascal. We go more, it's going to be 80 kilopascal, and so on. So as we go higher with altitude, the pressure will decrease. Okay, so it means that the number of moles of air will decrease as well as the height decreases, and the number of moles of air per unit volume, of course, will decrease, and consequently the number of moles of oxygen or the concentration of oxygen in the air is going to decrease. This will have a lot of impact on the activity of people who climb mountains or work at high altitudes will feel tired more quickly, because the oxygen is not enough in the air, or it's not as in high concentration as it is at sea level. So their bodies cannot get the energy that they need with the same rate. So they feel tired quickly, and also the car engines will be will operate at lower efficiency because of the lower oxygen concentration as well. There is one last thing here. This is an interesting video that I came across soon. This is a person who is riding a plane, and he has a potato chips bag, and he is monitoring how the bag shape will change at higher altitudes. So this, you can think of this as the same way we thought about, or we were discussing the tank. It has external pressure and internal pressure. The pressure inside the potato chips bag is atmospheric pressure. Okay, and as the the flight goes up, so he is showing here the altitude. The altitude here is 104,000 feet. Yeah, it's 104,000 feet. So it's a high altitude, and as the aeroplane goes to higher altitudes, the flight goes at higher altitudes. The bag now, the potato chips bags, it seems to be more filled with air. It's getting harder to squish, and as the flight goes to higher altitudes. And this is the interesting part. You see now this is the same potato chips bag, and you can see now it's very hard to squish, and it seems that it's going to explode. And the reason is what you see here is a reason of one very simple thing, that as you go higher with altitude, the pressure, the external pressure decreases. So it's exactly the opposite of what happened in the previous video for the tank. Instead of decreasing the inner pressure, we are decreasing the outer pressure, because we are going for higher altitude. So it seems that it's being filled with air. It's not actually filled with air. It's just exposed to lower external pressure. So this is a very, very, very interesting thing to know also about atmospheric pressure. So I hope these videos made the idea of the atmospheric pressure more clear, and how it has a very big value that is very effective. So I'll end this video here. Next video we'll have some problems to solve, just to practice more the concepts of fluid statics. So I'll see you then, inshallah. Goodbye.